Hey guys, this is chapter 1 of physics. It's our first chapter, first sections. I'm just going to introduce ourselves to the world of physics. There's a lot of different things that I hope you get out of the course this year. But I think the most important thing that I want you to walk away with a better understanding of is how to be more observant, how to take time to really process information. We live in a world where information is so easily accessible that oftentimes we forget to really process that information. You know, knowing how far the sun is from the earth, okay, it's just a number to so many of us, and yet that number should mean something. You know, how does that relate to the size of the earth? Or how does that relate to how long would it take me to get there if I'm traveling at the speeds that I'm used to traveling on the freeway? If I'm going 80 miles an hour, how long does it take me to get to the sun? Those are things that we need to maybe process a little bit more rather than just say, hey, here's information. We need to be a little more observant and really dig into that information more. Now, chapter 1 is really about setting the stage for us to be able to do some significant work in the world of physics, and so bear with me a little bit. It is a little choppy. And there's a lot of history that they go through in the text, which I think is definitely worth your time to read, but I'm not going to make everyone go through it in the video at the same time. I definitely would encourage you, though, to read a little bit about the work of Galileo, Aristotle, and the work that they did, other mathematicians, scientists like Newton and Leibniz, and the work that they did for us. What we're going to start with is understanding this idea of measurement and how we estimate things and how we evaluate things. And we know that the models of the universe and of the world, of atoms, have changed over time as we get more accurate measurement and become more detailed in our observations. That's something that was accepted a long time ago based on the observations that were present no longer makes sense because of new information, new observations. It's not that they just decided to throw out that the earth was flat, said, oh, it's no longer flat. It was about understanding that there is more information that contradicts that. And so we must come to a model or an understanding that makes sense. Now, this right here where it talks about physics and its relation to other fields. Okay, I want to make something very clear. I really do believe that almost all sciences, okay, are adapted or components of physics. You talk about chemistry. Well, that's a component of physics. Biology. It's physics applied to the human body. I mean, we have connections. Physics is related everywhere because of things like energy and mechanical structure and movement. It's hard to isolate a science that doesn't involve physics in some way. So even if you're someone who's really interested in life sciences like biology or anatomy and physiology, there's a direct connection to physics. And so we're kind of everywhere. You know, it's interesting, these two pictures. I try not to spend too much time talking about offhand stuff, but Roman aqueducts built over 2,000 years ago is in good shape, and yet we can have something that we build, you know, and a couple years later it falls apart because of an earthquake or because of just poor structural understanding and building. But we will cover everything from structural stuff to motion, to electricity, to light, sound, and so on. We're going to talk a lot about theories and laws. There are things called principles, and we can go through the definitions of those different things. I'm not going to worry too much about that. Where you are going to see some work in your homework today is this idea of measurements of uncertainty and significant figures. So when we go to measure something, like in this picture right here, okay, I have a mark for every millimeter on that ruler. The problem is, if it's in between those 2 millimeters marks, I can't say for sure what the measurement is. And so I need to acknowledge that when I take a measurement, I have accuracy to a certain degree. That idea of accuracy, or how close am I, okay, and the idea of precision, okay, these two different terms, they have a distinction in the world of physics. Probably in your everyday conversations, you probably don't notice the difference. But precision is in terms of how repeatable is it. So if I take the same measurement over and over and over again, do I get the same number over and over and over again? That would be precision. Accuracy is how close is it to the actual measurement. So when we say the actual measurement, let's say I use a laser to measure the length of a board. Okay, that's going to be extremely accurate. And then if I measure with a ruler, my accuracy is going to go down. It's not going to be perfect. I'm going to lose some of that accuracy. That being said, I might have a very precise answer with my ruler because I get the same number every time I use my ruler. Okay? We have this concept of uncertainty, which percent uncertainty is the amount of error divided by the actual measurement to give us a percentage. Okay? And that'll give us that idea. So the next thing that we kind of need to talk about is this idea of significant figures. So when we measure precision and we're looking at, let's say I've got a board here, okay, and I go to measure it. You like my little tracer, I like that. All right, so we go through here and we take this measurement, okay, and let's say my measurement comes out to be 3.2 centimeters. That means I'm measuring to the nearest millimeter. If I take that number and I want to say how many significant figures it has, I want to indicate how many digits are being part of my measurement. So the question is, did I actually measure the 3 centimeters? 1, 2, 3, and there's the 0.2. Let's call that. So there's my 3. Can I actually say I measured 3 centimeters? The answer would be yes. Can I actually say that I measured the 2 millimeters, the 0.2? And the answer would have to be yes. That's this mark right here, okay? So I can say those are measured numbers that are accurate and precise. This is an example of a number with 2 significant figures. Now, in the world of physics, as we go through and we do problems, it's important that we identify that we shouldn't manipulate numbers to appear to be more accurate than they actually are. Okay, so for instance, if I take that 3.2 centimeters, which, let's be honest, I couldn't measure more accurately than the millimeter with my millimeter ruler. But then somebody tells me they're going to add another board. I'm going to put a board to board, okay? I'm going to add an extra board here. And that this board from a factory was measured with a super precise measurement of 5.138 centimeters. I want to add these two measurements together. If I add them the way that they are, I would get 8.338 centimeters. But here's the problem. I don't know what happens after the 3.2. Is it 3.217? Is it 3.202? I don't know what should actually happen in those positions of my measurement. And so these two digits right here in my final answer would be claiming a level of accuracy that I don't actually have. And so we would want to reject these two digits, not because they couldn't be right, but because we have no way of knowing that we've done that part of the measurement that accurately. And so it's important that we understand when we go in and we do measurements and we do calculations with those measurements, we need to measure with the same number of sig figs or inaccuracy that we have at the beginning. So if something starts with 2 sig figs, we're going to answer with 2 sig figs. We're not going to just say, well, this number's super accurate. We're going to have to follow the accuracy that we're given. So that will force us to round sometimes, things along those lines. But keep in mind that if it starts with 2 sig figs, it ends with 2 sig figs. Now, a couple of things you're going to have to know about significant figures. For instance, if I say 0.5 meters, the question is that 0 in the beginning a measured 0? If you think about taking a ruler, the answer is no. We measure from 0, yes, but we'd only have measured to 0.5. So a leading 0 that is in front of a decimal, okay, not significant. So it's not a sig fig, okay? Let me give you a couple other examples. Let's say that I have the number 301. Was the 300 measured? Yes. Was the 010s measured? Yes, because it had to be in order to get this 1 measured. This is an example of a 3 sig fig. Guys, we kind of have to go through all the different parameters or examples to cover our bases. However, if I give you just the number 300, do you know for sure whether it was measured to exactly 300 or if it was measured to 300 and a little bit? We actually don't know. This one leaves us with a little bit of uncertainty. It could be 1, 2, or 3 sig figs. When there's a 0 that's trailing, not behind a decimal, so my decimal's back here, right? These zeros, I can't tell if they're placeholders or if they're significant. Okay. If you have questions, we're going to have them. We'll talk about it. There's some scenarios where you're like, oh, what about this and what about that? For instance, 3.0 times 10 to the third. That's a scientific notation. Scientific notation implies sig figs. Okay. If it was just 3 times 10 to the third, we'd have 1 sig fig. 3.0 is telling us we measured to that level. So again, you're going to say, Mr. Welch, this doesn't make sense. We're going to have to just talk our way through, look at the different examples. Scientific notation is a really good way to tell how many sig figs something has. Just a couple other real simple examples. I'm trying to take too much more time. If we have 2.5, that's 2 sig figs. If there's a 0, ask yourself a question. Does that 0 need to be there as a placeholder? The answer is no. So the only reason it would be there is to imply that it is significant. Okay? So we're looking for implications in the way the number is written. If a 0 can be dropped off with no impact to the number, and yet it's there, it must be significant. You'll get some practice problems with those that will hopefully help you figure some things out. Some of the basic measurements we use, obviously we use in the SI system, so we use meters, kilograms, and seconds. Those are our basic units that we're going to use a lot. So we have to use those units. We aren't going to use inches. We won't use feet, things like that. We'll convert them over if we ever have to use them. But yeah, time, mass, and length are our big ones. We do have prefixes. If you look over here on useful charts in the text, you can see right here, here's all the metric prefixes. So if you want mega, that's a capital M, it's 10 to the 6th. So a megameter would be 10 to the 6th or a million meters. And so you can kind of go through and find those if you need them. And let's go back to here. I'm trying to think if there's anything else real significant. Some unit conversion stuff. These are really good examples. If you have questions, I'd gladly go through them with you. But let me just do one with you really fast. That's a really common one that we're always doing in class. We're often trying to convert miles per hour to kilometers per hour or meters per second is more often. So let's say I'm going 80 miles per hour, and I want to convert that to meters per second, a unit that we use all the time in this class. What we're going to do is we're going to multiply by some fractions, one for each unit that we're converting. Since we need to convert miles, we'll start with the miles. To cancel the mi, or the miles, I need to have a mile in the bottom. So I need to know the conversion rate between miles and meters. I'm going to put a simple m there for meters. Well, it turns out that 1,609 meters is 1 mile. Okay? So that's going to convert or cancel my miles and replace that distance measurement with a meter. I want to do the same thing with hours, and so I'm going to take my hours, say that I have 1 hour, and I want to convert that into seconds. Well, 1 hour would have 3,600 seconds. So from miles per hour to meters per second, and there's my hours are going to cancel. If I take my calculator, which I know I have here somewhere, where are you at? Got to find my Wabbit emu. Oh, I don't see it. All right, we'll just use a basic calculator. You know what? We're going to use, we'll try it. This could blow up in our face, but we'll try it. Not what I wanted. Okay, do that, undo that. All right, let's go to scientific. All right, we're going to try this. We're going to take 80, I'm going to times it by, parentheses, 1609. Now that 1609 is being divided by 1, so I don't need to divide it. But then I'm going to times that by, parentheses, 1 divided by 3,600. And close my parentheses. And that gives me an answer of 35.75 or 35 point. So I gotta come back here and I gotta ask the question, what is my significant figures? 80 miles an hour. Let's assume that in the car when I'm driving that I'm measuring to the nearest mile, which would tell me I've got 2 sig figs. So I'm going to round this to 2 sig figs, which would give me 36 meters per second is the speed at which we're traveling when we're on the freeway. And that's how we're going to go about making some basic unit conversions. Hopefully that's enough to help you with whatever you're struggling with in class, and we'll see you in class.